welcome everybody to the 2021 Vermont Organics Recycling Summit, organized by the Composting Association of Vermont in partnership with the Vermont Agency of Natural Resources. This year's summit is being held during International Compost Awareness Week, the largest and most comprehensive education initiative of the compost industry. I'm Natasha Duarte, Director of the Composting Association of Vermont. I'd like to give a huge shout out to all of our sponsors. These include Community Bank, Eco Products, Vermont Natural Ag Products, Addison County Solid Waste Management District, AgriLab Technologies, EcoPixel, Nature Cycle, the Vermont Produce Program from the Agency of Agriculture, Food and Markets, and the Eco-AmeriCorps program from the Department of Environmental Conservation. Without their support, it'd be really hard to pull this summit off. So we really appreciate everybody's support. Before we get into today's program, I'd like to just make two announcements. The Composting Association of Vermont worked with Paul and Winsong Kervik to create a food scrap story calendar. The calendar features photographs of interesting designs that emerged in their food scrap bucket, and they took pictures throughout the year, and we put it together in this great little calendar. Inspired by what she saw in her grandmother's calendar, 4-year-old Neoma created her own food scrap art. Motivated by all of this creativity and interest from multiple partners, CAV is launching a statewide food scraps arts challenge as an outreach and education activity. Submissions will be featured on the CAV website, and some will be selected for the 2022 calendar. You can learn more about this project on the CAV website under projects. So now on to today's program. We're going to have opening remarks from Commissioner Peter Walk, and then we'll hear about the state of organics in Vermont from Josh Kelly, and then our featured keynote presenter, Dr. David Montgomery. Before I turn things over, I just want to also give a heads up that our first virtual tour is going to be at 3 p.m. today. And that features Vanguard Renewables Aerobic Digester at the Goodrich Family Farm. And with that, I'm going to stop sharing my screen, and I'm going to invite Bob Spencer, who is president of my board of directors, to come on and introduce our keynote speaker.
Hey folks, this is Bob in Vernon, Vermont. Josh, thank you. That was great. And we are so fortunate to have David Montgomery as our keynote speaker. He is a rock star of soil, dirt, composting, and as a professor at the University of Washington, he specializes in a wide range of organic recycling projects. And I'd like to just turn it over to you, David.
Bob, thank you. It's a pleasure to be here. Let me share my screen to get started here. And it's a pleasure to be talking to people who get it in terms of the importance of soil and composting and mulching and the kinds of things that you all do and some of the things that I'll be talking about today. What I want to do is to share with you some of my own intellectual journey in writing the 3 books that are up on the screen now, or at least hopefully you're seeing the 3 book covers that are up on the screen now. To give you an overview of why a geologist like myself would have spent so much time in the last 15 years sort of looking at, thinking about, researching the importance of soil, not only on an individual basis for a gardener or a farmer, but at a societal level and really for the whole human endeavor on planet Earth. I'm going to give you an overview of Dirt, the book that looks at the role of soil in human history. I'll give you much more on The Hidden Half of Nature, the book that I wrote with my wife, who's a biologist, that looks at the sort of the new science of what really explains why sort of the biology was the part that was left out of thinking about agriculture in the 20th century and why things like composting and mulching are so important to rebuilding soil health. What's the science behind that? And then also Growing a Revolution is the book that takes the lessons of that first book, the science in the second book, and looks at how rebuilding healthy, fertile soils can go a long way towards ameliorating not only agriculture's climate footprint, but also ensuring the future of soil fertility for coming generations. If anyone wants to get in touch with either Ann or I, our contact info is up there. I'll show it again at the end if you want to tweet with us or visit our website. But I'm going to give you the overview of these books. But the key factoid that I want to start with is really one that is very motivating to me. The estimates of how much of the world's soil has been degraded in terms of its fertilities over the course of agricultural history to date range from about a quarter to upwards of about a third of the available crop and grazing land in the world. But it's a problem that's still ongoing because the UN's Global State of the Soil Assessment from just a couple years ago concluded that humanity, the global us, so our collective endeavor on this world, we're losing about 0.3% of our ability to produce food each and every year to ongoing soil erosion, the loss of the soil itself, but also to soil degradation, which equates to the loss of soil organic matter in many ways. And that 0.3% number doesn't seem like a terribly large number considered in and of itself on any given year. But if you think like a geologist and play that out over the next 100 years, the balance of this century, for example, it adds up to roughly another third of the world's agricultural land will lose its productive capacity if conventional agriculture that degrades soil fertility maintains the trajectory that it has had recently over the balance of this century. And that starts to add up into fairly large numbers when you add it to the degradation of soil that's already happened globally. We're at risk of ending the 21st century with, on the order of half of the ability to feed ourselves that we potentially started the 20th century with. That's why a geologist would be concerned about the state of the world's soils and how we might actually reverse the pattern of historical decline. But that's not where I started. I'm going to start with the depressing part of the talk, because when you look back through history, there's a lot of examples in terms of how societies undermined their own longevity by degrading the very land that they depended on to grow food. And then turning that around is where composting and mulching comes into play a seriously central role in it. But first, I want to set the stage for why that is actually very important. If we look back through the history of agricultural civilizations, which is essentially the history of civilizations in the post-glacial world, we can document that soil erosion played a role in the demise of most, not quite all, but most ancient civilizations. And it ranges from Neolithic Europe or Bronze Age Europe to classical Greece, Rome, the southern United States, Central America, and other societies around the world. And if you're really interested in all the catalog of those and all the historical aspects of it, well, there'd be the book to start with. But what you normally find in environmental history textbooks is the idea that deforestation led to soil erosion that helped undercut ancient civilizations. And I took a bit of a different tact when I went and looked at what the actual story is in terms of land degradation around the world. In case after case, what I basically came up with was that it wasn't so much the axe as it was the plow that followed that resulted in degradation of agricultural lands around the world. It's sort of a different twist on an old story. And what is it about the invention of the plow that led to widespread soil loss and degradation in region after region around the world? Well, it fundamentally alters the balance between soil production and soil erosion. And that dramatically increased the pace of soil erosion and soil degradation, the loss of organic matter, as it turns out, as well. And this is something that, as a geologist, that's what I sort of trained to do in graduate school, to study the way natural erosional processes shape landscapes, shape terrain, what shapes mountains, how rivers move soil from the mountains to the coast and things. But as I worked for several decades studying landscapes around the world and how they evolved, I couldn't help but notice correlations between the state of the soil, the state of the land, and the prosperity of civilizations or societies, people that lived on that land. And that got me into sort of researching and thinking about and writing dirt, and looking at how it is that the history of agriculture has greatly impacted the course and fate of human civilizations through undercutting and undermining the fertility of the world's soils. And I'm going to try and cut this first part of the talk a little short from what I normally do, because you can always go read the book, and I want to get on to the microbes and composting part that comes next. But this one slide here of the Palouse region in eastern Washington really sets the stage for why a geologist like myself would look at freshly plowed fields as a erosional disaster just waiting to happen. This image basically shows you a winter wheat field in the Palouse region of eastern Washington in the 1970s. So it's decades after the Soil Conservation Service was established, decades after the Dust Bowl. But you can literally see the soil just washing off this landscape in those little channels that are known as rills. You could plow right over them. You could erase them with a single pass of the plow. So they're an agronomic nuisance, but they add up over time. What happens if they happen year after year? And what this is a winter wheat field in the fallow part of the traditional wheat fallow rotation in eastern Washington. And it shows you what happens when the land is left bare and vulnerable to erosion by water, by wind, water in this case. And that's essentially the Achilles heel of tillage, plow-based agriculture. It allows erosion to proceed at a pace that far exceeds the pace that soils build. And this is the second slide to sort of drive home the point in the Palouse of what happens if you allow that kind of erosion to happen year after year on a piece of terrain. This shows you a fence up in the upper right-hand corner. It's at the edge of this field where the farmer built a fence in 1911 to protect their water cistern from being plowed over and disturbed as part of their farming activities. The land surface in 1911, when this field was first broken for farming, was up at that upper orange line. By 1961, when the photograph was taken, it was down here at that lower line. Well, how high is that cliff, and what did it result from? Well, it resulted from year after year those rills forming when it would rain in the off season, when there was not a crop leafed out on the ground, and also from the progressive impact of the plow just pushing stuff downhill away from that fence year after year. Well, how high is that cliff? I haven't told you that yet. This little black bar here is a 1 foot increment on a stadia rod, on a survey rod. That's a 5 foot cliff. That's 5 feet of erosion that developed in just 50 years of conventional farming, of conventional tillage-based farming on this field in eastern Washington. That equates to about a foot a decade, which comes out, it's pretty close to an inch a year in terms of soil loss. And there's that happens to soils just don't form that fast naturally. And that illustrates fairly crisply the problem with plow-based agriculture, with tillage. It results in soil loss faster than nature can rebuild the damage. And this has happened in places all around the world. But I hope that you're sitting there going, well, Dave, isn't that just like one corner of one farm in a portion of eastern Washington? That could be a very extreme example. And of course it is. That's why I use it. It's the most visual and extreme example I can find to motivate the question. So let's step out and scale a little bit and look at the southeastern seaboard of the United States and look at agricultural erosion since colonial times. So this map shows you in that gray noodle, the Piedmont region or the upland region from Virginia down here to Alabama in the lower left-hand corner. So we're not talking about the coastal plain. We're not talking about the rocky spine of the Appalachians. This gray noodle was the hill country that was, one of the breadbaskets of the early American colonies in the Southeast, or the British colonies in the American Southeast, or in the early days of the American Republic. And what this shows you is the amount of topsoil loss that's been reconstructed by my colleagues down there in the lower right-hand corner since the advent of colonial agriculture in the region. And what it shows you is that more than 4 inches of topsoil has been eroded off pretty much the entire region. Notice the scale. It's 100 miles wide by about 800 miles long. This is a pretty big region. Parts of it have lost more than 10 inches of topsoil. How significant is that? Well, there are only about 6 to 12 inches of rich black earth over the red subsoil in this region to begin with. And when you visit the farms in this region today, you can see the subsoil at the surface across much of the region. When farmers are left to plow the degraded subsoil and are consequently, fairly addicted to intensive use of fertilizers to actually coax high harvests out of their degraded land. And this illustrates, what can happen over a fairly broad piece of terrain, and takes it out of the zone of, what happened in one corner of one farm in one state, to start thinking about, oh, this geography is, not all that different in terms of scope, scale, and size as the Roman heartland in Italy, or the heartland of classical Greece, areas that experienced substantial soil erosion and societal declines in previous civilizations. We've kind of repeated the exercise here in the southeastern United States. And this is what it looks like when you look at the soil. This is actually 2 soil samples from adjacent areas on a tobacco plantation in North Carolina. One of these 2 soils is taken from that conventionally managed tobacco field, where it's been treated with tillage and with intensive nitrogen fertilizer use for well over a century. And the other is from the forest immediately across the fence line, right next door, that had been a farm that was abandoned about 150 years ago and has gone back to be reforested with 3/4 of a meter diameter, 2-foot diameter trees growing on it now. And you can probably guess which soil came off of which field. The khaki one that looks like California beach sand with a whole bunch of crusty salt in it, that's the one that's off the conventionally plowed field. The one with a lot of organic matter in it from nature's composting and recycling efforts is the darker one that looks more like chocolate cake than California beach sand. What's the difference between these 2? Well, it's not the parent material. These are 2 soils developed on exactly the same geology, literally across the fence line from one another. It's not the climate. The climate doesn't change over those kind of small spatial scales. The difference is how people have treated the land for the last 150 years. It's about the effect of farming on the soil itself. And the color difference, that khaki color relative to that chocolate brown, that's carbon. Soil organic matter is roughly 50% carbon. And so what's happened on these soils is that nature has essentially rebuilt soil organic matter over the course of a century and completely transformed the nature of the soil at that spot. Which of these soils would you rather be working as a farmer? I have yet to meet a farmer who would choose the one that is actually from the conventional farm. It's a very telling example that soil degradation is not just about the physical loss of the soil, all those little rills and the erosion that I was showing you in previous slides. It's also about converting organic matter rich soil into organic matter poor soil. And that's essentially what's been done on farms all across North America, and indeed around the world. There was a paper that came out in the journal Sustainability roughly 5 years ago that looked at the degradation of North American soils, what's happened and how it might be mitigated. And the take-home message for me in that review paper was the highlighted sentence down here at the bottom. The soil organic matter content of many soils in North America is only about 50% of the level at present at the time they were converted from forests or prairies to farmlands. In other words, we've burned down roughly half of the amount of carbon in soils on North American farmlands. That plantation from North Carolina I showed you is not unusual. It is more it is more common than we are likely to believe or understand. That same number, roughly about a 50% degradation of organic matter, is typical for cropland soils around the world. It's essentially the equivalent of having run down the batteries of our the farm soils we depend on, by about half in just a couple centuries of conventional farming. But I also looked in Writing Dirt to make one last comparison about how fast soils are eroding from farms around the world. So I basically went into the library for a month and gathered up every research paper I could find that documented a rate of soil erosion off of modern farms. And the global average that I came up with was about 1.5 millimeters a year as a global agricultural soil loss. That means that it takes less than about 20 years to erode an inch of fertile topsoil at that pace. You know, 1.5 millimeters a year seems like a slow number. Your fingernails, or at least my fingernails, grow faster than that. And yet, when you think about it geologically, or think about it in the context of the nature's ability to rebuild the soil, it becomes frightening to think that we're losing an inch of topsoil on average around the world in just a couple decades of farming. Because how fast does nature make soil? That's the other thing that I researched in putting the story together. And the average rate I came up with was about 2% of a millimeter per year. At that pace, it takes 1,000 years or so, centuries, to make an inch of fertile soil, to remake that inch of fertile soil that conventional farming can shed in just decades of farming practices. Therein lies the basic problem with mistreating soil at a global level today. And what I've just given you is all the numbers that you would need to calculate for yourself in the back of a napkin what the average longevity of an agricultural civilization might be predicted to be if this was an important effect globally. That net soil loss of roughly 1 millimeter a year implies that you could erode off a 0.5 meter to 1 meter thick hill slope soil in just 500 to 1,000 years. That it would take 1,000 years plus or minus 50%, say, to actually limit the longevity of an agricultural civilization that way. And when it turns out, when you look around the world, that's roughly the average longevity of agricultural civilizations, with a couple major exceptions. And those, of course, are the major river floodplains of the world. Places like the Tigris and the Euphrates in Mesopotamia, the Nile in Egypt, the Indus and the Brahmaputra in India, and the big rivers of lowland China. Those are all areas where we know farming has been sustained for thousands of years. And there's been a continuity of agricultural civilizations in those places, but they're kind of the exception that proves the rule. Because when you think about all those geographies, they share something in common. They're big river floodplains. And what happens on big river floodplains? Well, they flood. What comes along with the water? Silt, sand, and clay. And if you think about the size of a single grain of sand, they range from about 0.5 millimeter to 2 millimeters in size. And that's basically spans the range of the average rate of topsoil loss off the world's farmlands. In other words, if you're on a big river floodplain, the deposition, and you allow flooding to occur, the deposition of a single grain of sand a year can essentially compensate for the erosive effects of tillage. And that's how civilizations have been able to maintain their continuity over the long run, even with using practices that can degrade the soil over the long run. Now, this is where I'm going to pivot from the depressing part of the talk to the more sort of optimistic end of things, and it's where microbes and composting and mulching starts to come into the story. Because when you ask the question of, is soil restoration possible? Could we actually reverse the historical pattern of declining soil fertility? That's obviously the question I was asking myself as I started to finish writing Dirt, and I was getting a lesson right under my own nose in my own backyard from my wife, who's a biologist and a gardener. And we wrote about our experience in The Hidden Half of Nature together in restoring fertility to the soil in our yard at a pace that far exceeded anything that I could find in the academic literature for how fast nature can make soils, and started me on the road to optimism about that we could completely turn around the problem of soil degradation, but it would take thinking differently about the soil and treating organic matter and organic wastes very differently than we have in the past. So the hidden half is one that tells both Ann and my story. And it starts when we bought this house in North Seattle where we live. And it came with a side yard that had this old growth Seattle lawn. It was basically single species lawn that wrapped around the house. The people who had the house before us for 80 years apparently were not much into gardening, but Anne saw this as a blank slate to actually build the dream garden that her biologist mind had always wanted to have ever since we were graduate students. But it ran into a major snag when we peeled that lawn back to reveal the nature of the soil that we had. We had this khaki soil. It looks like that North Carolina tobacco plantation. It's soil that had been stripped of organic matter when they developed the house. And when we pulled that lawn off, it was just a tangled 6-inch thick mat of roots. There wasn't a single worm beneath that lawn, no visible life that we could find at all. It was a mix of glacial till and fill from the originally leveling out the lot. And we both bemoaned, why didn't we think to dig a soil pit in the yard to test what was beneath the hood of the lot? We paid an inspector to inspect everything about the house, but we didn't think to actually dig a hole in the ground, even though I've done this all around the world to study soils. The good news on that is that Anne didn't think to do it either, so we're both equally to blame. And she put her biologist mind to the task of, well, how could we actually improve our soil? We have all the mineral matter we need. What we were lacking was the biology. We were lacking the worms and the organic matter and the microbes. And just notice the neighbor's house back here. That peak will show up in a slide in a few minutes. But Anne decided that what we needed was to compost and mulch the hell out of the yard. Frankly, she underwent what we called her organic matter crusade, convincing neighborhood arborists to give us their wood chips and dump them, yards of them in our driveway. We started composting and mulching, and ferociously trying to add organic matter to try and bring the soil back to life. And what are the kinds of things that we did? Well, in an urban environment like Seattle, sort of in the days before there was as much awareness of the importance of composting and mulching and organic matter recycling. Today, I'm happy to say that Seattle has the materials that we don't choose to compost on site, the city will compost for us. But back when we were first starting to restore our yard, that program was not in place, and Anne took matters into her own hand, doing things like experimenting with wood chips and compost, or adding seashells to her wood chip and compost mixture. We also got stuff that's known as Zoodoo, which you can probably guess what it is. It's the composted herbivore turds from the Seattle Zoo that the Seattle Zoo invites people to submit postcards, and in those days, they invited people to submit postcards for a lottery to see if you could get Zoodoo. And by the third time that we won the Zoodoo lottery and was able to load up my pickup truck with Zoodoo, we realized that it really wasn't all that hard to win the Zoodoo lottery. They wanted you to take the stuff, and it was just magic for the garden. We also used, fresh leaves and grass to get mixtures of nitrogen and carbon, fresh pine needles as a carbon source, and started really experimenting with creating different kinds of mulches and different kinds of composts, treating it much the way that she treats cooking in the kitchen, as sort of an improvisational chef. So, for example, she would take her wheelbarrow painted up with racing stripes, courtesy of some help from a local auto body shop, and basically do things like add the clippings from our hinoki trees, our neighbor's bouquet that they would give us. So yes, beware, if you give us flowers, they will end up in the compost at some point. Shrub and tree leaves and decaying wood chips. She really experimented with different types and amounts of compost, and also composting our kitchen scraps, composting coffee grounds from the neighborhood coffee shop, and brewing up compost tea with a bubbler and an inoculant, and really trying to work to restore life and fertility to the yard by reintroducing the organic matter that had been lost through the glacial history of Seattle, but also then the development that basically scraped the soil off, just like the glaciers had done before when they actually built our house back in 1918. And what we noticed as a result, fairly quickly as a result of all her composting and mulching activities, was that we started to rebuild healthy, fertile soils. This shows you her pruning shears that after just about 3 or 4 years into composting and mulching, that khaki soil we started with is now buried between a couple inches, about 2 inches of actually halfway decent looking soil with more compost and mulch up on top of it. Notice what the plant roots are doing. They're growing through the good stuff and they're stalling out and going sideways when they get back to that glacial till, the soil that we really started with. We started to see a real difference in our soil within just a couple years. And after 10 years of composting and mulching, Anne was able to turn the soil that we started off with, it started off like this khaki colored stuff that looks a lot like that North Carolina tobacco plantation, and had less than 1% organic matter if you don't count the wood chips that we layered on it on top. She turned it into stuff that has about 10% organic matter. And the difference in that, it's soil, it's organic matter, it's carbon. We were able to we calculated that we've added, literally tons of carbon to the soil in our yard simply through composting and mulching over a decade of intensive gardening. And what it did to our garden was even more impressive than what it did to our carbon footprint. Notice the peak of the neighbor's house over here. Today we have a vibrant garden. We noticed that when we restored fertility to the soil, the plants just exploded out of the ground. And the kale plants got up to half of Anne's height in the vegetable beds in the garden. It was really sort of a magical transformation that changed our lives as well as the life in the soil. Because what we realized is that we were doing the composting and mulching, but that wasn't where the real work of transformation was going on. It was happening below ground, because that compost and mulch that we were adding to the surface of our soil was getting worked down into the soil and integrated into the soil food web as it was being consumed by organisms that would shred it and mix it with the soil, and the bacteria and the fungi that would eventually decay that organic matter would then in turn be eaten by nematodes and protozoa and microarthropods, that their manure would essentially micro manure the soil from the inside out, because bacteria and fungi are incredibly rich in things like nitrogen and phosphorus. They're little fertilizer bombs, they're little fertilizer packets. And they were all this biological activity that got reinitiated in our soil was really what was behind the change in the organic matter content. It was things like these shredding beetles that would rip the leaves up that the trees were dropping on the beds and that would rip into our compost. The worms that were mixing the organic matter and the mineral matter together in our soil. And the microbes, the bacteria and the fungi that were at sort of the final stage, if you will, on that decomposition process of returning the biological matter back into the soil and converting it into forms that new life could take up and add to their bodies. And the nematodes that would eat bacteria and microarthropods that would graze on fungi or bacteria, their manure was essentially what was a big part of what was helping to increase the organic matter content of the soil. And so Anne and I started looking into the soil life and the soil food web and thinking about what happens in relationships between plants in the soil and life in the soil. And as we dug into that, we started to get beyond the understanding of root systems that we had learned in graduate school and soil sciences classes in graduate school that portrayed roots as straws, essentially, that suck up nutrients from the soil to deliver to plants. We all know that plants will take in carbon dioxide to build their bodies through photosynthesis, and they produce oxygen as a result. But one of the things that we didn't know in terms of looking into this was that plant roots are a two-way street. they not only take up water and nutrients and minerals from the soil, but they also exude compounds into the soil. And what are they exuding out of their roots? Carbohydrates, proteins, lipids, fats. What does that sound like? Carbs, fats, and proteins. That sounds like food. Plants basically are pushing food out into the soil to feed microbes in the zone called the rhizosphere, literally Greek for the zone around the roots of the soil. So the zone around the root system. And if you look at this famous photograph of a seedling, the sort of the yellowish stuff are the actual roots, the whitish stuff are the mycorrhizal fungi that have partnered with that plant and linked up to those roots. And plants produce exudates, sometimes of which can account for 30% of what they capture through photosynthesis. They'll ooze that out into the soil in ways that are intended to feed the microbes living in the rhizosphere. And that sets up what we termed the biological bazaar, in which if you zoom in around a single root coming out into the soil, and the rhizosphere being that sort of purple zone, the plants are putting those exudates out into the soil, those food for microbes, and they don't make it more than about 1 millimeter to 1 centimeter out away from a root or root hair before a life form will eat it. The zone around the root systems of a healthy plant are some of the most life-filled areas on the planet. And those bacteria are taking in those exudates, consuming them, and they're metabolizing them. And what do they make? Well, metabolites. They make their own waste products. But those waste products, those metabolites, can be things like plant growth promoting hormones. So those bacteria in the soil are eating the photosynthetic products that the plants are exuding into the soil, and they're creating compounds that benefit their host organism, that make it grow bigger, that enable it to capture more solar energy, enable it to produce more exudates, to feed more microbes. That's essentially a virtuous circle. It's a mutually beneficial or symbiotic relationship. Similarly, fungi in the soil will partner with the plant root, go off and extend their fungal hyphae out into the soil and attach to either organic matter or mineral particles, and mine things like phosphorus or zinc out of the soil, mineral particles, bring them back, trade them to the plant for essentially plant food, because what fungi can't do, they don't photosynthesize. They're saprophytes. They can eat decaying organic matter or organic matter that a plant that can photosynthesize provides to them. So this opened our eyes to understanding a great network of relationships in the soil, where fungi will go out and fetch mineral particles from the soil, trade them back to their host plant in exchange for a cut of their sugary exudates. And the role of soil life in plant defense and plant health also follows from that role of exudates, because turns out that, what would you do as a plant if you were stuck in place? You can't walk around, so you can't flee from a predator. And if an insect starts chewing on you, what might you do? Well, many plants have evolved the strategy of putting out exudates into the soil that recruit very specific microbes that produce metabolites that the plant can take up, that then either it triggers that plant to produce a chemical compound that makes the plant repel that insect pest, or they produce a compound that itself repels the pest that the plant takes up and makes the plant taste bad, sending the insect off to a less healthy plant. Turns out that relationships with soil life are central to the defensive strategies of plants. Yet when we look at in typical botany textbooks for looking up, say, the principal parts of a vascular plant, we pay attention to the flowers and the leaves and the above ground stuff, the stuff in the part of nature that we can see with our own senses as we're walking around the ground. And often the root system is relegated to sort of the smaller sort of piece of the study or piece of the puzzle. And Anne likes to say that this image, this picture, that's fake news. It's not really the way it works. The underground part is really as important as the above ground part. We like to look at the foliage above ground, but the real sort of intelligence system of a plant, in the sense of the system that it uses to gather information about its environment and its world and shape its response to that is really in the root system. So we like to superimpose the image of a brain on the image of the root system and the fungal hyphae network connected to it, to basically illustrate that there's an awful lot of interaction and intelligence that happens in and around the root system of plants. That's where a lot of the action is. And that's where, if you look at the root and its relationship to the soil, a plant that's growing in sort of dead soil that has very few microbes in it doesn't have as many allies in the soil as a root that's actually growing in a microbial rich environment with lots of life and potential allies in the soil that can help shield it from pests and pathogens. If you think of how a root a pathogen would attack this root, it's got an open door to actually get it at it in the dead soil, but actually to get at a root in a microbiome, in a root zone, in a rhizosphere microbiome that's filled with life, there's a lot of competition that can basically screen out pests and pathogens from actually attacking that root. And so, which is the smarter plant? Well, one that has a well-developed root microbiome. It gets more intelligence in the sense of information from its environment, and that allows it to better react to and adapt to its environment. And so the idea of practices that support healthy life in the soil really make a difference to the health and growth of crops, and actually to human health as well. Ann and I are working on a new book on that will be out probably next year. But here what I want to do is focus on sort of differences in what this biological bazaar means to the health and growth of plants. We all know that we can grow sort of large plants on what Ann and I call the fertilizer diet, and you can do it in fairly degraded soils. If you add enough nitrogen, phosphorus, and potassium, NPK, to the soil, you can get large harvests. You can spur a lot of biomass growth. But what do you lose out on? Well, you lose out on those micronutrients that the fungi were fetching and delivering to plants, and you miss out on those beneficial microbial metabolites that turn out to be important for maintaining plant health. What do you get instead growing plants in an organic matter rich soil? They tend to invest more in their root system because they're basically putting more into recruiting microbial partners in the soil, producing more exudates. And you can also get comparable harvests, but with using less fertilizer and using sort of organic forms of fertilizer that act like drip fertilizer into the soil rather than a fire hose of fertilizer. But that also deliver micronutrients, minerals that turn out to be important for plant health, livestock health, and human health, and also beneficial microbial metabolites that are also very instrumental in plant health. And so we think that it's no coincidence that in the 20th century, the global sales of pesticide went through the roof after global sales of chemical fertilizers, of N, P, and K, because we essentially dismantled the natural defensive systems of our primary crops in agricultural settings by degrading the soil, turning organic matter rich soil into organic matter poor soil, and relying on chemical fertilizers to goose yields, as opposed to so we ended up with high harvests and poor plant health. The soil health diet is what we've termed sort of growing plants in an organic matter rich environment. And there's parallels that we see between this root system and its interrelationship and symbioses with life in the soil and what happens in the human digestive tract, because our relationship of the host organism with the microbiomes, the microbial world in both settings, are very parallel. And we make the case in the hidden half of nature, but that essentially the human gut is very much like the rhizosphere, just inside out. The two systems, the role of microbial symbiosis with the host organism functions very similarly, just with different directionality in those two systems. But in both systems, Those partnerships that are fueled by by organic matter in both settings, what we eat in the case of the human gut and soil organic matter in the case of the soil, help with the host organism acquire nutrients that provides also beneficial microbial metabolites that are the key to plant defense, and also it's central to the ability of the human immune system to ward off pests and pathogens. And so our relationships of host organisms and our microbiomes in these two systems are really different than the way we've tended to think about microbes. And it puts into perspective the importance of their care and feeding, of providing the organic matter to feed soil life and to provide the sort of the plant matter that helps feed our own internal inhabitants as well in our gut microbiome. And if you're interested in the parallels between those two systems, again, I recommend The Hidden Half of Nature. We go into that. But one of the take-home messages that I wanted to pursue after writing The Hidden Half with Anne was to look at whether or not the methods and techniques she used in our yard to restore the soil to our yard, with the key on composting and mulching and feeding the beneficial life in the soil, whether that could work on full-scale commercial farms. How can we turn this kind of khaki soil into this kind of black dirt, richer black organic matter rich dirt? This shows you the effect of what Ratan Lal has done at the Ohio State University using intensive farming practices to rebuild healthy, fertile soils. And I took about 6 months off after finishing writing The Hidden Half of Nature with Anne to visit farmers around the world who had done what she had done to our yard and what Ratan Lal had done to his experimental farm at Ohio State, and visited farmers in Africa, Central America, across North America. Unfortunately, we ran out of funding before I could visit farms in Asia, but the same principles apply there. And what I found is that the farmers who had been very successful at rebuilding the organic matter content of their soil followed what are known as the principles of conservation agriculture. And that involves minimal or no disturbance of the soil. So they were either direct planting their seeds in variants of no-till farming. So they stopped plowing. And they were maintaining a permanent ground cover with cover crops that retained crop residues. So they were using cover crops and basically making mulch on site. Some of them were also using compost that they would prepare, particularly some of the African farmers. And they were also adopting diverse crop rotations that helped to break up pathogen carryover. If you just keep growing corn in the same field year after year, you're going to invite corn pests to a banquet. If you diversify one's crop so that the same crop is not following the same crop, it really disrupts the ability of pathogens to carry over. Those three principles in common were the ones that I found that the farmers that I visited who had been very successful at restoring their soil on their farms had adopted all three. It wasn't enough to just do one or two. It was the full system of three that really worked. And why did that work? Well, that first one, minimal disturbance, if you can stop disturbing an organism, it can allow it to thrive. Tillage really disrupts fungal networks in the soil. The permanent ground cover part, that's where cover crops, compost, mulching, feeding the soil organic matter comes into play. And diverse rotations can provide a diversity to that underground microbial bazaar. It just turns out, though, that those three principles are virtually the opposite of what we've taught in agronomy for most of the last 100 years, where we've relied on intensive tillage, agrochemicals, and specializing in one or two crops, functional monocultures. So it's a different way of thinking about the act of farming that maps right onto what you would do to support the microbial life in the soil. What all those little microbes are there to remind me to say is that this is a recipe for essentially feeding the life in the soil. And this, how does this work on farms? I'll share just a couple examples with you before I wrap up here. This gentleman here is David Brandt. He runs Brandt Family Farm in Carroll, Ohio, and he grows wheat, corn, and soybeans for the North America commodity markets, but he also grows a lot of various cover crops. This tillage radish he's growing here is not destined for the farmer's market. He grows them to terminate and let rot in the soil because they basically are a way to build up organic matter and cycle it and use that to feed subsequent crops. That feeds networks of fungal hyphae is apparent from just picking up a clod of soil from his fields. They're shot through with fungal hyphae. His neighbor's fields are not. How did this work for him? He basically adopted that package of no-till cover crops and diversity to not to his cash crops, but to his cover crops. And over the course of 20 years, he turned soil like this that he started with back in 1971 into the soil that he had the year before that I visited him in 2015. It's the same soil, the Cardington clay soil. It's a heavy clay soil, and he took it from sort of a percent or so of organic matter back up to about 6 to 8% organic matter, comparable to, if not a little higher than the native soil that his region had when it was forested. And he did it all the while as an intensive, commercially viable farm. In fact, his farm is more profitable than his neighbor's farms by substantially, because he has greatly cut his use of diesel, fertilizer, and pesticide as he restored fertility to his soil. The other farmer that I'll mention briefly is Gabe Brown, who is both a farmer and a rancher in Bismarck, North Dakota. And he basically practices regenerative agriculture, the style of agriculture that integrates those three principles that I was talking about. But he's also brought livestock back to the land and is engaging in regenerative grazing to rebuild the health and fertility of his soil. And he'll bring his livestock in to graze off his cover crops. And then chickens in to graze the flies that sprout from the cow pies that the cows use. He's basically using the cows to rapidly recycle his cover crops into manure that then feeds organic matter into the soil, feeds the life in the soil. And he likes to say that he's now, instead of buying fertilizers and pesticides, he's basically selling beef and eggs. It's much better for his bottom line. How was he able to pull off the transition? Because the practices that he's adopted changed his soil from stuff that was, halfway decent to begin with into really rich black earth. This is actually the soil on his neighbor's farm. This is the soil on that field that I just showed you. The difference is carbon, soil life. However way you cut it, if you look at returning life to the soil, follow the carbon is really kind of the message. And that's where composting and mulching comes in terms of urban environments, as environments that produce a fair amount of organic waste that unfortunately in many regions is still ends up in the waste stream. And we're basically taking what is an incredibly valuable resource and wasting it that way. That's why I'm so thrilled and happy to see the progress that Vermont's making in terms of your organic matter handling policies and protocols. You guys are really leading, and it's wonderful. I sort of step back and take the global view of, what are some of the benefits of rebuilding soil health globally, both in terms of repurposing our urban organic waste, but also in terms of how we can grow a mulch on site on farms and integrate that into a revised set of farming practices. There's a lot of benefits that could flow from it. We can get comparable or increased crop yields. I didn't go into the yields of the farmers in this talk that I visited in Writing Growing Revolution. The details are in the book, but to a person, they were they were meeting or exceeding the yields of their conventional neighbors after just a couple years of an initial transition period. So they were basically harvesting as much, and they were using a lot less fossil fuel and pesticide and fertilizer to do so. that resulted in much higher farmer profits. And that's what really started to turn me into an optimist in terms of thinking about the global potential to restore soil health, is it's starting to make a lot of sense economically to rebuild the health and fertility of our farmland and revert and turn around that process of degradation that I started the talk with. And of course, that can result in increased soil carbon, which can have a big benefit in terms of climate resilience, but also in terms of crop resilience, because more carbon in the soil translates into better water retention in the soil, but it also translates into less pollution getting off the site in terms of nitrates and phosphates. The simple, single best way to reduce nitrate and phosphate pollution in water wells, streams, rivers, the Gulf of Mexico, is to essentially use less of the highly soluble chemical fertilizers that have so dominated agriculture today. Only about half of them actually ever gets into a crop. The other half runs off. These regenerative agricultural practices and conservation agricultural practices that they're rooted on can really reverse and turn that around. So I think that today we're basically poised for what I hope to see as what I like to call the fifth agricultural revolution, one based on soil health. And there's a huge role that the repurposing of urban organic matter, urban organic wastes can play in that global effort. So I thank you for your attention. I obviously recommend the books, and Ann and I are currently finishing up a book that looks at the effect of soil rebuilding and soil health on human health. The question of what do these agricultural practices that I've been talking about, and what does restoring health and fertility and life to the world's soils, what might that mean for what's actually in the food that we consume? And hopefully that'll be out next spring. We're literally in the process of final edits on it. And so, Natasha, I think I'll probably hand it back over to you at this point. And if we have time, I'm happy to engage in any questions.
Yeah, thank you so much, David. That was a fascinating talk. And I personally am really looking forward to your upcoming book that sort of blends that soil health and human health aspects together, which are two topics that I spend a lot of time working in and thinking about. We do have about 10 minutes. If people have any questions, feel free to go ahead and type them into chat, or raise your hand or type into chat that you'd like to be unmuted, and we can do a little verbal Q&A if that's easier for folks. One of the things, David, I'll just maybe start us off, that a lot of the stuff we've been talking about in regenerative agriculture and the economic sense it makes, and the soil health benefits, the human health benefits. How do you, I guess sometimes I applaud your optimism, and I'm mostly there with you, but sometimes I just feel like, why aren't we moving the needle a little faster? And just with your travels that you've done and interviewing and talking to so many different farms and different communities, I just wonder if you might share your optimism about how we could actually more broadly change some of these practices.
Well, there's a number of factors that play into sort of hesitancy for farmers to actually adopt more of those practices. Mm-hmm. But before I get into those, let me just sort of step back and sort of comment that back when I was writing Dirt back in the mid 2000s, 2006 was sort of the end game of trying to write it. There was hardly anybody talking about soil health. There weren't soil health conferences. It was something that, a few people in the organic or biodynamic movements were very, very, very concerned about and very good at addressing, but it hadn't really sort of achieved sort of widespread buzz, shall we say. there's now all kinds of people thinking about it, talking about it. The whole regenerative agriculture movement has really sort of sprung into being over the course of that time. So when you think about it from a geological perspective, that's really fast. So, part of my optimism is rooted into sort of seeing that these processes that degrade the soil and that can rebuild it, they play out over a fairly long period of time. And so I personally think it's going to take us decades to get to the point where what I call regenerative ag practices are become conventional practices and are adopted widely. But I see great momentum behind it, and a lot of it coming from farming communities. I've spent more time in the last 10 years speaking at farming conferences in the middle part of this country than I ever thought I would do. As a geologist who studies mountains, I thought I'd be spending time in the Alps and the Himalaya. And I've spent a lot of time in Montana and Kansas and the Dakotas talking with farmers about their soil and the global importance of it. And I've seen a lot of real enthusiasm for reinvesting in and rebuilding the health and fertility of their soil. But, of course, I've been talking to people who are receptive to the message, right? Because those are the people who will invite me to talk to them. Some of the barriers I've seen are, first, force of habit. It's really hard to get anyone to change the way they do things. And I'm as guilty as anybody else in my daily habits. And so it's very difficult to come and sort of tell someone, the way you've been farming for 50 years, well, it turns out that that's probably not the best way, and you should probably change it up in a pretty serious way. You're going to meet a lot of resistance. What I started to become more of an optimist about was when I realized how time and again, when I would go visit some of the sort of early adopters and pioneers of regenerative agriculture, people who'd figured out how to make that system of principles work as practices in their area for their crops, that they were more profitable than their neighbors, and because their neighbors are paying more for diesel and patented seeds and fertilizers. And if they're harvesting about the same, well, the regenerative folks were spending a whole lot less to make that same income. And it's the difference, the spread on the bottom line, that really matters for profitability. And so when I started to see sort of the lights go on for myself and farmers who had adopted these kind of practices, that if you think about profitability instead of yield, it makes a lot of sense to go with these more regenerative methods. I think that's going to spread and catch on, but I think it's going to take time. In a way, I look at my own sort of field in academia where, sort of big ideas sort of have a lifespan, if you will, about equal to the lifespan of a person's career, 30, 40 years. Because why? Because the way we're trained tends to shape the way we think. And so when I go now to talk at some of the big agricultural colleges around the country, the faculty are often kind of split as to whether I'm talking crazy talk or whether I'm talking the next wave of real insightful things. The grad students all want to go out for beer afterwards and talk about regenerative agriculture. So I think we're going to see a generational shift in the way people tend to think about the soil. And that's not to say that, old guys like me aren't on board with thinking about the changes. But part of what makes me an optimist is I think that enough of the science has come together pretty solidly in the last 10 or 20 years behind, why regenerative practices work, why biology needs to be reintegrated into our thinking about soil health. That the people that are trained going forward are going to be much more receptive and creative and innovative in terms of how they figure out how to do it. So, and the final bit of an answer to that is, I choose to be an optimist. I consider it a more healthy lifestyle.
Excellent. We did have one question come in asking if you might speak a little bit about water and structured living water versus chemically treated water and the impact that has on I'm ad-libbing here a little bit, Paul Kervick, so jump in. But the impact that the quality of water has on the life in the soil, which translates into the life of the plant and as well all the way through to human health, right?
Yeah, that's a good question. I mean, here
Mhm.
in Seattle, I can occasionally smell the chlorine in our tap water. And I sort of
Mhm.
wonder, what's that doing to my microbiome when I drink that water? And I
Mhm.
don't know. I can't get it out of the water.
Yeah.
The I have not looked a lot into what that does. I've looked more into what restoring health to the soil does to water quality, as opposed to what water quality does to soil health. So I can't give you a whole lot of guidance or insight into that, other than there's nutrient load issues in water, and so that part of the problem with nitrates and phosphates are too many nutrients can disrupt aquatic ecosystems in a pretty serious way. They also disrupt soil ecosystems in a pretty serious way. But most of what I've looked at is in terms of drought resilience, in terms of restoring fertility to the soil and how that can really help retain water in the soil. The simple answer in terms of, I think, water quality, from my perspective, is that the cleaner the better. Nature as a farmer basically evolved to use rainwater, which is pretty darn clean, and other than the kind of stuff that we can put into it. So yeah,
Sure.
I'm not going to provide you a whole lot of insight onto that question because I haven't looked into it a whole lot.
Great. And Paul, I do see your hand raised. We're just going to take one other question, and then we'll circle back to you, Paul, just to try to get some different thoughts here. Emma asks, how did some of the farmers you spoke with first start to practice regenerative agriculture and to change their practices?
Yeah, that's a great question. I sort of tell the story of about 5 or 6 of them in the book that goes into that, but almost to a person. They started off through a financial crisis. They were basically sort of backed into it because they ran out of money for fertilizer. Or Gabe Brown tells the story about how he was hailed out 3 or 4 years in a row and was starting to go broke, and he had to just figure out a different way that didn't cost so much to actually keep putting out each year for inputs. And the ones that I visited were people who I had met at conferences who I knew had already sort of restored fertility to their land. And so they were some of the initial adopters. They all had different paths to getting there, but most of them went no-till first, and then they started adding cover crops, and then they started to diversify. So none of them actually adopted the full system of 3 principles, the no-till, cover crops, and diversity, straight out of the gate. They learned how to put that all together. And if you look at how 2 out of those 3 principles, the cover crops and diversity, those are not new ideas. I mean, those go back to traditional agricultural practices all around the world in terms of, integrating legumes into one's cropping and diversifying and having a crop rotation. Reintegrating animal husbandry with cropping, if done right, is also a big soil builder. And the ideas on that go back centuries as well. What's really, I think, new about the whole sort of regenerative agriculture movement is the idea of combining those traditional practices with the no disturbance, with no-till. And one of the big ironies of this all is that, one of the biggest impetuses for adopting no-till in North America was the development of the herbicide glyphosate, which made no-till a very easy practice for made weed control simple with no-till. So I devote a lot of time in Growing Revolution to talking about, well, what are the other ways to control weeds in a no-till system, and how can you have sort of an organic no-till systems be productive and do it without the herbicides. And it's putting those sort of 3 principles, that adding that new dimension of minimal disturbance to the cover crops and diversity, that I think really works. And it's because of that, you don't disturb the organisms, you feed them, and you give them partners to partner with. That's a recipe for cultivating the beneficial life in the soil, which helps you suppress the pests and pathogens and also helps you have more productive soil with fewer inputs.
Great, thank you. And so we had one other question come in, but I'm gonna just circle back to Paul Kervick and ask you to go ahead and unmute yourself, Paul.
Yes,
And,
hi.
Yeah.
Hi, Natasha and David. Wonderful presentation. I'm so impressed.
Thank you.
Thank you. Thank you very much. And Natasha for hosting this conference. Yeah, I come at from a human point of view, and basically on a cellular level, we're 99.997% water. The kind of water in our cells is key to absorbing nutrition, getting rid of toxins. And this is the same in soil. And some of the farmers, I'm now working with a group out of California, the Hydration Foundation, and Dr. Jerry Pollack's work around the world, looking at restorative agriculture and the impact by using structured living water, which is just, it's got extra hydrogen. It's H3O2, it's not H2O, the way most of us think about water. So it actually has this electrical charge, which will stimulate and activate from the bacteria to the rhizomes and the roots to the plants, nutritional value. And the farmers and studies we've been doing in Texas right now, they've shown an increase of 30% in, I think it was production, and also a reduction of 30% of water usage. So it's like, if you're hydrated, you're going to perform better. If our plants and soil is hydrated, it's going to perform better. And so right now we're wanting to actually work with Natasha and find a couple of farms here in Vermont to do a demonstration project with, I'm going to get your book, David, because restorative agriculture, the soil part is important. We're working with organic microbes, but also bringing in this water technology that is not real expensive to be able to implement that in a farm for irrigation and hydration. So that was it. But thank you so much. Appreciate it.
Well, Paul, thank you for your comment. Yeah, I've focused mostly on the soil end of things because that's sort of where my background is from geology, but I'll be curious to see what you find at that.
Great, thank you, Paul. And I think we have time for one more question that had come in, asking if you hope, David, that healthy soils and composting will play a role in climate change mitigation.
Yeah, no, I think that can play a large role. I think the idea that the rebuilding soil organic matter can completely offset fossil fuel emissions, I think, is sort of overselling the idea. But I go into sort of at the end of Growing a Revolution, I go into the sort of the carbon building aspects and how much I think we might be able to actually put back in the world's soils. And it's a large amount that could equate to, a quarter to a third of current emissions over the course of many decades, should we adopt these newer agricultural practices at a global level. So I see sort of rebuilding soil, and that's just looking at cropland. If everyone did it in the yard the way we did it in our yard as well, you could add more to that. And the numbers in terms of how much it could be are fairly controversial. Different scientists will argue at the lower end or higher end of different ranges, and there's a lot of variables that go into it, and there's a lot that's unknown at the present in terms of how much soil organic matter can be rebuilt. But I've seen enough farms now where the regenerative farmers have built their soil organic matter level back up to higher than the native soils in their region, to think that, what is the limit? It's not that clear to me. What is clear, though, to me, is that there's the big role that soil restoration can play in climate mitigation, both in terms of capturing carbon through photosynthesis and parking it in the soil where it can do us more good. But also, I view it as sort of a win-win-win-win in the sense that the kinds of practices that we would do to build soil organic matter as a carbon sequestration or storage strategy are the same practices we would use to rebuild soil fertility to help feed the world, the same practices we would use to try and more efficiently use the water that falls on our fields in a drying climate in different regions, and also the same practices that we would use to try and restore biodiversity to our farms. And as Ann and I are writing about now in the book that will hopefully be out next spring, it can also help reintroduce elements of nutrition to the human diet that have been compromised through modern conventional agriculture. And so we're trying to pull all those threads together. And it's my contention that any one of those benefits would be worth sort of thinking about pursuing. But when you put them all together, you can kind of think of the climate part as the bonus. So whether it's at the low end of the ranges that academics argue about, or the high end of the ranges that many advocates maintain, wherever it ends up falling in that range is a net benefit to society and to our global endeavor of feeding ourselves and maintaining civilization on this planet. So I think we should be restructuring our agricultural incentives and policies to basically encourage as much soil building as possible for the next 100 years, and just challenge ourselves to see how much we can do, because I think it could really add up.
Great, thank you. And that I'll just share a comment from Susan Alexander that soil building strategies are also now supported by the subsidies provided by USDA NRCS, which is also just another layer of making it more attractive to conventional farms to actually experiment with this and to try to get movement here. So
yeah, NRCS has been very supportive of the idea of building soil health.
Yeah, it's great. And so I also would encourage everybody who may not know so much about the NRCS programs to go ahead and check that out on their website as well. We are unfortunately out of time, but thank you so much, David, for starting our summit off on an optimistic and very interesting note. And thanks as well to Josh Kelly and Commissioner Walk for the early part of this session. And with that, thanks again, David. And thank you everybody for participating and taking time out of your day. And we hope to see you soon.